Hi, this is Dr. Allaire from the University of Houston downtown. And in this video, we are going to break down quiz number 4. Quiz number 4 focuses on the Science Teaching Competencies 7 and 8, which gets us into the physical sciences. Now, before we get into this breakdown of quiz number 4, there are a couple of very important differences that I just want to cover very quickly. First and foremost, as you've probably realized, there are not 5, but 10 questions in this quiz. That's right, folks. Okay, and that's because there was so much great science wrapped up in competencies 7 and 8 that it was just impossible to pick 5 questions that were representative of these competencies and really do them justice. So instead of sticking with 5 questions, we expanded the quiz out to 10 questions. Now, that doesn't mean that this quiz is worth 10 points, and that's because each of those questions is worth half a point. So the overall quiz is still worth only 5 points. The other difference that I want to mention here is that previously, the questions for our other quizzes came strictly from study guides made for the Texas core subjects. That's exam 391. However, the difference here, starting with this particular quiz, quiz number 4, is that yes, some of the quizzes come from those study guides for the core subjects test, but some of the questions also come from previously released versions of the 5th grade STAR exam for science. So as teacher candidates who are seeking early childhood through 6th grade certification, 5th grade falls into that category, which means that you may at some point be tasked with teaching students and preparing them for the science exam that gets done in 5th grade for STAR testing. And so it seemed reasonable to me to include those questions. So we've got 10 questions to get into. So stick with me during this video breakdown as we go through quiz number 4, question by question, exploring all of this great science content that's wrapped up in each of these questions and getting into some of the test-taking strategies that you might want to use when you take your certification exam. So let's get into these questions. First of all, if this looks a little bit different from how you took the quiz in Canvas, do not be alarmed. I am using a program called Socrative to go over the questions together. So please, again, do not be alarmed if this looks a little bit different from what you saw on Canvas. First and foremost, okay, so number 1, if a model car takes 2.55 seconds to go around a 3-meter track, its speed would be. So this is very simply what my science teachers liked to call a plug and chug problem. And so first of all, you need to know the formula for speed. Speed equals the distance that an object travels divided by the time it takes to go that distance. So this is one of those formulas that is really handy to know. We see it all the time without realizing it. This is how we measure our speed in our cars, whether it's on the speedometer or if you look at a speed limit sign that we in Texas tend to ignore. But again, regardless of how you're measuring it, if you want to measure speed, you are taking the distance that something travels, miles, kilometers, whatever, divided by the time it takes to go that distance. So seconds, hours, minutes, what have you. So now we plug in our numbers to figure out the answer. So the really big part of this problem is not just knowing the formula, but plugging in the numbers correctly. So remember, distance is on the top part of the fraction, that's the numerator. Time is on the bottom part of the fraction, that's the denominator. So our distance is going to be 3.0 meters divided by 2.55 seconds. And if you didn't set this up correctly, then that is going to lead you down a pathway that you don't want to go. And so now we just do our math. But wait, before we do the math, I want to talk about some test-taking strategies here because you don't even really have to do the math in order to figure out this problem. You just have to think about how it's set up. So 3 divided by 2.55. Because 2.55 is smaller than 3, because the denominator is smaller than the numerator, we know that 2.55 is going to go into 3 at least one time. So that means that 0.85 meters per second, there's no mathematical way that that can be the answer. So we can go ahead and cross that out. At the same time, there's no mathematical way that 2.55 is going to go into 3 7 times. So we can cross out the letter D in this case, 7.65 meters per second. And what we're left with is a choice between 1.18 meters per second or meters per second squared. So yes, the numerical answer is going to be 1.18, but now we need to figure out the units. And the way we figure out the unit is by combining what's in the numerator and the denominator. And since the unit in the numerator is meters and the unit in the denominator is seconds, our unit is going to be meters per second. And that is how we get the correct answer, which in this case is the letter A, 1.18 meters per second. So going on to question number 2, student 1 pulls a wagon to the left with 40 newtons of force, and student 2 pulls a wagon with 25 newtons of force, on the same object to the right. So here is our diagram. We see student 1 and student 2 pulling in opposite directions, one to the left, student 2 to the right. Student 1 again pulling with 40 newtons of force, student 2 pulling with 25 newtons of force. What is the total force pushing or pulling on the object, and in which direction will the object move? So this is a problem that's about figuring out the net force. So the net force is the total amount of force acting upon an object. And so just as a refresher, a force is simply a push or a pull acting on an object. So for instance, as we're all sitting here on planet Earth, Earth is enacting a force on us. It is pulling us down. So gravity is always working on us. We don't notice it except when we trip and fall. And so the net force, again, is the total amount of force acting upon an object. So here is our diagram. We've got 40 newtons of force pulling to the left. Actually, I'm going to move this object here. I'm going to put it here, 40 newtons of force to the left and 25 newtons of force to the right. The newton, by the way, is the unit that we use to measure force. And so we very simply are going to combine these forces. Now, if the forces were moving in the same direction, we would add them together. But since they are moving in opposite directions, their net force in this case is we are going to be subtracting. So 40 newtons minus 25 newtons. Our net force is going to be 15 newtons. But it's not enough to just have a number. We also need a direction. And the direction is that it's going to move in the direction of the larger force. And the last time I checked, 40 was bigger than 25. So 15 is going to be moving to the left. The 15 newtons of force is going to move to the left. So looking at our answers here, again, our answer choice is A, 15 newtons to the left. We are not adding these together, so we're not going to be getting 65 newtons. The object is going to move because these forces are unbalanced. We have student 1 pulling with more force than student 2. And yes, there is enough information in order to figure out the answer to this particular problem. Question number 3. Students build a balloon rocket car using a balloon, a straw, a water bottle, and some tape. When the straw is released by a student, we can see our diagram here of the water bottle with the student pinching on the straw. When the straw is released by a student, the air from the balloon comes out. A diagram of the car is shown. Which statement best describes the motion of the car when the straw is released? So once again, here is our diagram. We've got all of our air trapped inside of the balloon, creating lots and lots of pressure in here. It wants to get out. It wants to escape. So when we release our fingers here, when the student releases his or her fingers, that air is going to come out of the straw, pushing in this direction. So the air is going to blow to the right, which means that the car is going to go in the opposite direction. It's going to go to the left. And so looking at our answer choices here, our best answer choice is going to be the car will move away from the hand and towards the wall because of the force of the air from the straw. A is incorrect because it says the car will move away from the wall in the same direction as the air that is leaving the balloon. That is incorrect. Remember, as the air comes out one way, the car is going to move in the other way. The car will move fast because the straw gets light as the air is released. Nope, that's going to be incorrect. The car will not move because the air escapes from the balloon. We hope not. Number 4, which of the following is a sign that a chemical reaction or a chemical change has occurred? So all of these, A, B, and C, changes in shape, melting, and dissolving, these are all physical changes. Okay, so it's important to kind of review some of these terms. A physical change is a change in the shape or state of matter for an object. Maybe a better way to say this is for a substance. But the substance stays chemically the same. Okay, so for instance, if I was to melt ice that came out of my freezer, the ice is melting, it's changing its state from a solid to a liquid. However, it's still made of the same stuff. It's still made of water, H2O. All right, dissolving, not necessarily a sign of a chemical reaction. Change in shape, not necessarily a sign of a chemical reaction. If I take a piece of paper and I crumple it up into a ball, I've changed the shape of that paper, but I have not performed a chemical reaction. However, if heat is given off or absorbed, meaning that something is getting hot or it's getting cold, that is an indication usually that a chemical reaction or a chemical change has occurred. By the way, I think let me take a moment to define chemical change. That would be a change in the chemical makeup of a substance. In other words, something new is created. All right, so I just wanted to take a moment to go over that definition. Number 5, chemistry is all around us. Which of the following is not an example of an everyday chemical reaction? Melting butter onto popcorn. As I mentioned before, melting is an example of a physical change where something is changing its state of matter from a solid to a liquid, but it is chemically the same. Whereas photosynthesis, cellular respiration, and rusting metal are all examples of chemical reactions. Number 6, a student poured equal amounts of water and cooking oil into a jar. The student placed a lid on the jar and shook the mixture for 5 seconds and then let the jar sit for 10 minutes. The results of this investigation are shown. So let's take a look at this diagram here. Again, they put equal parts water and cooking oil into a jar. They put a lid onto the jar and they shook it around. So here is a diagram of what it looks like immediately after shaking for 5 seconds. They let it sit for 10 minutes, and here are the results. The cooking oil has settled on the top, the water has settled on the bottom. Which conclusion best compares a property of cooking oil and water shown in the investigation? The best answer here is that cooking oil is less dense than water. How do we know that it's less dense than water? Because it is floating on the top. Things that density is a measurement of the amount of stuff packed into a space. And so the more dense a substance is, generally speaking, the heavier it's going to be. So when it comes to liquids, the denser liquid is going to settle to the bottom, while less dense liquids are going to be on top. And cooking oil is less dense than water, so the cooking oil is going to be on top. That's the only correct answer to this problem. Number 7, a student is classifying objects. Answering which question will provide the best evidence that an object is a metal. So our choices are, does it conduct thermal or heat energy? What is its mass? What is its physical state? And how quickly does it dissolve in water? The only question here that is going to give us any kind of evidence that something is a metal is, does it conduct thermal or heat energy, or even electricity for that matter? Measuring the mass of the object is not going to determine whether it's a metal or not. It's not going to help us determine if it's a metal. What is the physical state? Generally speaking, metals tend to be solids at room temperature. However, mercury is an exception, although I hope that you are never encountering mercury in a classroom situation. But mercury is a liquid at room temperature. Also, some metals, such as gallium, have very low melting points. So they will actually change from a solid to a liquid around about your body temperature. So you could actually hold gallium in your hand and it would melt into a liquid. How quickly does it dissolve in water? That's not going to help very much because metals, along with a lot of other substances, do not dissolve in water. So again, in this case, the only question that's going to help us identify whether this is a metal or not is, does it conduct heat or thermal energy? Number 8, which of the following is not an element? I'm a big fan of the periodic table, as you can tell from my background here. And so, in fact, I think you should always keep a copy of the periodic table close to your heart because chemistry is more important than life itself. So this is a simple recall kind of a question, asking which of these is not an element: argon, gold, salt, or hydrogen. The only correct answer here is salt. So it's important to know what an element versus a compound is. An element is a substance that is made of only one kind of atom. So argon is made only of argon atoms. Gold is only made of gold atoms. Hydrogen is made only of hydrogen atoms. Same goes for oxygen, helium, carbon, fluorine, meitnerium, mercury, iron, cadmium. Any element that is on the periodic table is made of only one kind of atom. Now, a compound is a substance that is made of 2 or more kinds of atoms. And that's why salt, particularly table salt, is the answer to this question, because the formula for ordinary everyday table salt is sodium chloride, NaCl, meaning that it's made of one atom of sodium and one atom of chlorine that are chemically bonded together. That's what makes this a compound, and that's what makes it the answer to this question. Number 9, a student conducts the investigation shown in the diagram. So here we have 2 chairs standing back to back. We have a piece of uncooked spaghetti suspended between them with a string, a cup, a paper cup tied to it, and that can hold various things, pennies, washers, whatever it is. In this experiment, a paper cup hangs from a string tied to a single uncooked spaghetti noodle. The student measures and records the mass of a penny. The student then adds pennies to the paper cup one at a time. Which question is the student most likely trying to answer in this investigation? Is it A, how much force will it take to break the spaghetti noodle? B, how long should the string that holds the paper cup be in order to support the greatest mass of pennies? C, how does the distance between the 2 chairs affect the amount of force it takes for the spaghetti noodle to break? Or D, how many spaghetti noodles will it take to hold up the mass of a penny? So this is, before we reveal the correct answer here, I just want to also, kind of like going back to the first problem, we can do a little bit of process of elimination here, because there are the potential for multiple correct answers. And what we need to figure out is the most correct answer. So first of all, there is one answer choice that we can eliminate immediately, and that is answer choice B. How long should the string that holds the paper cup be in order to support the greatest mass of pennies? One has nothing to do with the other. Okay, so the string is really not going to do anything as far as supporting the mass of the pennies, because what we're really looking at is the noodle to support the mass of the pennies. So we're left now with three choices. And so C, so first of all, D could potentially be an answer, except that, you know, we're kind of making an assumption here, and we always hate to assume. But it looks as if we have maybe a single, it says here, tied to a single uncooked spaghetti noodle. So perhaps this could be an extension where we look at, you know, what happens if we have two uncooked spaghetti noodles for 3 or 5 or 10? What effect does that have on the number of pennies? But because it tells us explicitly that there is a single uncooked spaghetti noodle, we can rule out answer choice D, because that information is just known. How many spaghetti noodles will it take to hold the mass of a penny? And we can assume that it's going to, you know, at least one noodle will hold 1 penny. So we're left with a 50-50 shot of how much force will it take to break the spaghetti noodle, or how does the distance between the two chairs affect the amount of force it takes for the spaghetti noodle to break. And the more correct answer in this case is going to be the letter A, because even though, yes, the distance between the chairs is going to have an effect on it, there's nothing mentioned in the problem about the chairs being movable or mobile, or a measurement of the distance between the chairs. So that leads us to believe that A is the most correct answer here. Although, again, C is a potential question that could be answered through this kind of experiment, and even D is a potential question that could be answered through a different kind of experiment. But for this particular experiment, the best answer is going to be A. And let me delete those. There we go. Last but not least, rounding out quiz number 4, Mr. Martinez has his students conduct experiments to investigate friction. Friction is the resistance to movement. So if you, for instance, rub your hands back and forth, you can feel heat from your hands because the friction between your hands is resisting this motion. And the faster you rub your hands together, or the more you press down on them, the more friction there's going to be. So which experiment will best test the effect of friction on objects? And the best experiment, the best answer in this case is going to be the letter B, where his students are rolling 3 marbles across 3 different surfaces from the same starting point at the same time with the same amount of force. And I'm going to take a guess here that the marbles are around about or very close to the same size and mass. And so the key piece of information that really makes this the correct answer, first of all, is all these things are the same, but then also that we have 3 different surfaces involved. Okay, for A, roll 2 marbles on the carpet from the same starting point, the same time with the same amount of force. Again, a lot of things are the same there, but because they're both on the carpet, we're not really investigating the effect of friction on the objects. Dropping 2 balls from the same height. Well, yes, air resistance is a type of friction. There's nothing in the description here to suggest that we are looking, for instance, at 2 different sized marbles, a very small marble and maybe a very big marble. And letter D, release 2 balls from the top of a ramp at the same time. That's a really great general description of an experiment that could be done. But once again, because it doesn't say anything about the surfaces, we're really not looking at the effect of friction on the objects. And that's why B is the best answer and the correct answer to number 10. Well, that's going to do it for quiz number 4, covering Science Teaching Competencies 7 and 8. Again, these are the first 2 competencies for physical sciences. So now we are starting to get into the science content with our quizzes. As always, if you have any questions, please do not hesitate to email me, message me, or talk to me before or after class. Thanks so much for watching. I'll see you soon.